Okay, so thank you very much. Before I start, I'd like to thank the organizers for inviting me to speak here today and for organizing this wonderful conference. I've really enjoyed myself so far, so thank you for that. Okay, so today I'll be telling you about some joint work with Jersun and Anna Wienhardt about the Goldman symplectic form on the PSLV Hitchin component. Okay, so let me begin by recalling what is the PSLV Hitchin component, which actually Ursula introduced in her talk yesterday. Okay, so let me begin with some notation. For the rest of today, I'm going to let S be a closed, connected, oriented surface of genus at least 2. Okay, and gamma is going to denote the fundamental group of S. Okay, I also let V denote an n-dimensional real vector space. Okay, where I'm going to assume always that n is at least 2. All right, and this is the V in the title. Okay, and I'll denote the Teichmüller space of S by TS. Right, we've seen this a couple of times already in this workshop. And as Karsa said, you can think of this as the deformation space of hyperbolic structures on your surface. Okay, so all the essentially different ways you can equip your naked topological surface with a hyperbolic metric. Okay, but I'm also going to think of this from a different point of view, from a more representation theoretic point of view. Okay, and this is the set of discrete and faithful representations rho from gamma to PSL2R, which is the group of orientation-preserving isometries of H2. And I consider these representations up to PGL2R, up to conjugation in PGL2R, right, which is the isometry group of H2. Okay, the advantage of thinking of Teichmüller space from this representation theoretic point of view is that it admits a higher rank generalization. It admits a generalization to the setting where I replace my target Lie group with PSLV instead of PSL2R. Okay, and that is what the PSLV Hitchin component is. Okay, to describe this more formally, I need to rely on this fact that Ursula also mentioned yesterday. Okay, there exists a unique, up to conjugation, irreducible representation, which I'll denote by iota from PSL2R to PSLV. Okay, and this is a very concrete thing. You can actually describe this explicitly using the Veronese embedding. Okay, but I'm not going to do that here today. If you've never seen this before, you should think of this as some canonical way to put PSL2R into PSLV. Okay, and what this gives us is embedding of Teichmüller space into the space of homomorphisms from gamma to PSLV. And I'm going to consider these representations up to conjugation in PGLV, right, the group of projective transformations on V. Okay, and what is this map? Well, I take any point in Teichmüller space, which I'm thinking of as a conjugacy class of representations. Okay, I choose a representative in this conjugacy class. I post-compose it with this irreducible guy, right, to get something that goes from gamma to PSLV, and then I take the conjugacy class in here. Okay, and you can check that this map doesn't depend on any of the choices I make. So it's well defined, and this brings us to our definition. The PSLV Hitchin component, which I'll denote by HitVS, okay, is the connected component okay, of this space here, where is it here, okay, which I'm going to denote by XV of S. Okay. That containing the image of I. Okay, so here I'm using the fact that the Teichmüller space is connected, right? So since this is connected and the map I is continuous, the image of I in XVS is connected, so it makes sense to take the connected component of this space containing the image of I. Okay, another way to say this is that the Hitchin component is a set of representations in XVS that you can continuously deform to a representation in the image of I. Okay, and this guy here is known as the Fuchsian locus of the PSLV Hitchin component. Okay, so this is the object I would like to study. Now, when V equals to R2, okay, then you can check, it's not so hard to see from the definitions that the PSLV Hitchin component is exactly Teichmüller space. Okay, so this follows from the well-known fact that the Teichmüller space is a connected component of its character variety. So it is in this sense that I'm thinking of the Hitchin component as a generalization of Teichmüller space. Okay, and then the first kind of general result about the Hitchin component was a theorem of Nigel Hitchin, who used Higgs bundle techniques to show that this space here, the Hitchin component, is real analytically diffeomorphic to R to the n squared minus 1 times 2g minus 2. Okay, so this generalizes the well-known fact that the Teichmüller space is a cell of dimension 6g minus 6. Okay, and furthermore, this says in particular that the Hitchin component is a real analytic manifold. Okay, it does not contain any singular points of your character variety. Okay? Now, one reason why people care about the representation in Teichmüller space is because we understand a lot of the, they have a lot of geometric meaning, right? They all arise as holonomies of hyperbolic structures on your surface. Okay, and but when Hitchin proved his theorem, it was not known whether the representations in the Hitchin component had any geometric meaning. Okay, so there was a problem until François Labourie came along, and he proved the following theorem. Okay, he showed that every PSLV Hitchin representation, right, which is a representation in the PSLV Hitchin component, is a Nosov. Okay, so Ursula defined for us what this word means yesterday, but if you didn't absorb completely what she said, right, you should just think of this roughly as saying that all the PSLV Hitchin representations have a lot of good geometric properties. Okay, so for example, in particular, they are all quasi-isometric embeddings from gamma equipped with the word metric into PSLV equipped with any left invariant Riemannian metric. Okay, so this is saying that if you take any PSLV Hitchin representation, the way that it puts gamma into PSLV preserves the coarse intrinsic geometry of gamma. Okay? So this is the Hitchin component, right? It's a connected component of your character variety, consisting only of smooth points, and where every representation in there has very good geometric properties. Okay, so this is the space you would like to study. Next, I would like to talk about the Goldman symplectic form. Okay, so this is a symplectic form that you can define in a pretty general setting, right? You can define it on a set of smooth points of any character variety of representations from a closed surface group into a reductive Lie group. Okay, but for today, I'm just going to define this for you on the Hitchin component. All right, so to define this as symplectic form, you need to use two observations by Goldman. Okay, the first is a very general fact, okay? The tangent space to the Hitchin component at any point, rho, right, is canonically identified, okay, with the first cohomology of your surface, with coefficients in SLV, okay, twisted by the representation ad of rho. Okay, so SLV here is the, okay, let me just aside. SLV here is the Lie algebra of PSLV, but you can also think of this as the set of traceless endomorphisms. Traceless linear maps from V to V. Okay? So if you're not familiar with first cohomology with twisted coefficients, you should just think of this as some cohomological description of the tangent space at every point in the Hitchin component. Right, and then the second observation is the following. Okay, first I'm going to consider this bilinear pairing B on the Lie algebra of PSLV, so on SLV. Okay, so how is this bilinear pairing defined? I'm going to take any two endomorphisms traceless endomorphisms. I'm going to compose them. Okay, so this gives me another endomorphism of V, but this might not be traceless anymore. Okay, so I take its trace. Okay. So this bilinear pairing turns out to be a non-degenerate, symmetric, and invariant under the PSLV action on its Lie algebra by the adjoint representation. Okay, so if you're familiar with Lie algebras, this is just a multiple of the killing form on the simple Lie algebra SLV. Okay, so it has all the properties that I just mentioned. Okay, and using this, you can construct another bilinear pairing, which I'm going to denote by omega, and this is defined on the tangent on the first cohomology of S with coefficients in SLV twisted by arrow. Okay, so this bilinear pairing is defined in a two-step process. First, I'm going to send this to the second cohomology of my surface with real coefficients. Okay, and how do I do this? Well, if I give you two first cohomology classes on the surface, right? The kind of usual way you get a second cohomology class is to use the cup product. Okay? However, because my coefficients are in SLV, and these are twisted in SLV, if I just take the cup product, what I'm going to get is a second cohomology class on my surface with coefficients in SLV at row tensor SLV at row. Okay? If I want to get real coefficients, I need to pair the coefficients here some way, and that's where this bilinear pairing B comes in. Okay? It allows me to pair the coefficients to get something in R. Okay, and here I'm using the fact that B is invariant under the adjoint action of PSLV on SLV. So once I get something in here, then now I can take the cap product with the fundamental class of my surface. Okay, so remember my surface was closed and oriented, so there's a canonical class in its second homology, which is this guy. Okay, and so here I'm just pairing the second cohomology class I get with the second homology class here, and then you get a real number. Okay, so Goldman observed that this guy here is actually a symplectic form. On the PSLV Hitchin component. Meaning that this bilinear pairing is non-degenerate, skew symmetric, and if you view this as a two-form on the Hitchin component by defining this bilinear pairing at every tangent space using this canonical identification, then this two-form on the Hitchin component is a closed two-form. Okay? So when V equals to R2, okay, then the Goldman symplectic form here is half times the Weil-Petersson symplectic form. On Teichmüller space. Okay, so you can think of this as a generalization of a very classically studied symplectic form. All right, so the question that I would like to address in this talk is what does omega look like on the PSLV Hitchin component? Okay, so this is a very vague question, but fortunately we have some guiding theorems on Teichmüller space to tell us what we should be looking for. Okay, so the theorem I'm referring to follows from the work of, it's a theorem of Scott Wolpert, okay, who was working on Teichmüller space. So I'm going to suppose that V equals to R2. Okay, then he says that for any Pence decomposition, P on my surface S, okay, the Fenton-Nielsen coordinates associate on Teichmüller space associated to P are global Darboux coordinates. For the Weil-Petersson symplectic form omega. Okay, what does this mean? This means that the Weil-Petersson symplectic form, as a two-form, right, it can be written as the sum from I equals to 1 to 3g minus 3 So I'm summing up over all the closed curves in my Pence decomposition of dLi where's d theta I. Okay, where Li and theta I are the Fenton-Nielsen length and twist coordinates associated to the ith closed curve in my Pence decomposition. Okay, so if you choose a Pence decomposition on your surface, then this gives you a natural coordinate system that's very explicit on the Teichmüller space, and you can explicitly describe what this symplectic form is in terms of the coordinate functions of this coordinate system. Okay, so if you have a symplectic form, this is as explicit as you can get. Okay, so this was partially generalized to the setting where n equals to 3, when the dimension of V is 3, by Hong-Chang Kim. Okay, which this was done in the mid-90s. In the case where n equals to 4, by Hong-Teck Zhang. And this is pretty recent work, and I don't think it's completely written down yet. Okay, and the main technique they use here is this procedure known as Fox calculus. Okay, so this was actually a technique that Goldman proposed in his paper where he introduced the Goldman symplectic form as a way to algorithmically compute the Poisson pairing of functions associated to the Goldman symplectic form at any smooth point of the character variety. Okay, so what they did is they executed this algorithmic procedure to try to prove an analog of the Wolpert theorem. Okay, there's one big drawback with this procedure though, which is the computations you need to do to execute Fox calculus gets really complicated really fast. Okay, so for example, if you look at the case where n equals to 3 at Hong-Chang Kim's paper, it comes attached with this huge mathematical file, okay, a pretty big mathematical file that you need to verify in order to understand its proof. Okay, I don't know if people have done that. Okay, and even in the case where n equals to 5, right? So not so much higher than Teichmüller space, that nobody knows how to use these kind of techniques to prove a theorem like Wolpert's. Okay? So this was the state of the art before our paper. All right, so, okay, so I guess that's all the introduction I wanted to give. And next, I'm going to move on to talk about some of the results that we proved. Okay, but before that, any questions, comments, objections? No? Okay. So instead of using this Fox calculus technique, right, the approach you are taking to understand the Goldman symplectic form is more like the approach that Bunohan and Sauzen took, right, which was the theorem that Kasra mentioned yesterday. So our approach is similar to Bunohan, Sauzen on Teichmüller space. Okay. So before I tell you anything, I need to tell you how to make some topological choices on my surface. Okay, so I'm going to let T be an ideal triangulation. On S. Okay. And J is going to denote a compatible bridge system. Okay, so I will tell you what these two objects are in a second. But before I do that, I want to emphasize that these are purely topological objects. Okay, I can define, once you give me the fundamental group of S, I can define them entirely. However, if you further choose a hyperbolic metric on the surface, then you can actually realize these topological objects as geometric objects on the surface. Okay, so what I'm going to try to do is explain to you what their geometric realizations are. Okay, so I'm going to choose a hyperbolic metric, sigma on S. Okay, so sigma is going to denote S equipped with a hyperbolic metric. Okay, so here's a picture of my hyperbolic surface. Sigma. Okay. Now, what is an ideal triangulation on this surface? Well, it's a way to cut your surface into hyperbolic ideal triangles using finitely many simple geodesics. Okay? So if you want to do that on a closed surface, you necessarily need to use some closed geodesics. Okay, so you need to pick some, you start with some closed geodesics, closed simple geodesics like these. Okay, but of course, this does not cut your surface into ideal triangles, right? So what you need to do is you need to keep throwing in simple but non-closed geodesics that kind of spiral onto the closed geodesics. Okay, so you have something that looks like this. And on this side, it kind of does something like this. Okay? And then you just keep adding in these non-closed geodesics in a way that doesn't intersect the geodesics you already have on your surface until you cannot anymore. And what you end up with is an ideal triangulation. Okay, so these guys have some names. The orange curves, the closed ones, are called closed edges of my ideal triangulation. And the non-closed ones are called isolated edges of the ideal triangulation. Okay? So if you look in the universal cover of my surface, right, so this is isometric to the Poincaré disk. Okay, and I lift all the geodesics in my ideal triangulation onto the universal cover. What I'm going to see are the lifts of the closed geodesics, the closed edges. Okay, so there are infinitely many of them, but I'm just going to draw two. And then you're going to see lifts of these isolated edges that kind of accumulate onto the closed edges. Okay, so you're going to see a picture that looks something like this. Okay. Okay, so something like this. So this is what an ideal triangulation looks like. Okay, what is a compatible bridge system? You should think of this as a compatible bridge system as a choice of a short transverse arc across each closed edge. Okay, so if you lift it to the universal cover, or the orange, okay, what you're going to see is a gamma invariant choice of these short transverse arcs across the closed edges. Okay, and what this is doing really is it's picking out a pair of ideal triangles, one on each side of the closed edge. Okay, so that both of the ideal triangles you pick share a common vertex with the closed edge. Okay, so for example, this guy here, this bridge, right, picks out these two ideal triangles, and they both share this common vertex with the closed edge. And on this side, let's say you look at this bridge, okay, this picks out two ideal triangles. The guy on the left shares this common vertex with the closed edge, and the guy on the right shares this common vertex with the closed edge. Okay, so this is what a bridge system is. Okay, so with this, we can already state our first theorem. Yeah, right. So what this is, another way to say this is a geodesic lamination with finitely many leaves. Okay. Okay, so the first theorem that we prove is the following. Okay, you make any choice of an ideal triangulation and a compatible bridge system. Okay, then this choice determines a symplectic trivialization of the tangent bundle to the Hitchin component. Okay, in other words, there exists a symplectic vector space which I'll denote by W sub t. So it depends only on the ideal triangulation of my surface. And a symplectic isomorphism of vector bundles which I'll denote by C of Tj. It depends on both the ideal triangulation and bridge system. Okay, from the tangent bundle to the Hitchin component to the product of the Hitchin component and this symplectic vector space Wt. Okay, and both of these are viewed as bundles, symplectic bundles over the Hitchin component. Okay. So I should remark that this theorem is not just an existence theorem. Okay, everything here can be described explicitly. I can explicitly tell you what is the symplectic form you choose on the vector space, and I can explicitly tell you what this map is. Okay, but that involves lots of notation, so I'm not going to do that here. Okay. But in any case, with this theorem, it makes sense to talk about the next definition that I'm going to give you. Okay, so definition: a Tj parallel vector field right? It's a section so on the Hitchin component. It's a section of the tangent bundle to the Hitchin component that is parallel with respect to the flat connection induced by your symplectic trivialization. Okay, another way to say this is, well, you look at this vector bundle first, okay? And you can consider the constant sections, right? The ones that assign to every point in the Hitchin component the same vector in Wt. Okay, and then you pull those sections back to the tangent bundle using this map, and the sections you get that way is called the Tj parallel vector fields. Okay? So, right, so the next theorem I would like to describe to you gives a description of what these Tj parallel vector fields look like in terms of a real analytic parametrization of the Hitchin component. Okay, so in order to do that, I need to mention a little bit of the work of Bunohan and Dreyer. Okay, and what they say is the following. Okay, so you make the same choice as I did, right? You choose a T and a J. Okay, then you let K be the number of closed edges of the ideal triangulation T. Okay, so you count the number of orange curves you have in your ideal triangulation. And then they say that there exists a convex polytope denoted by Pt inside of R to the n square minus 1 times 2g minus 2 plus k times n minus 1. Okay, I'm going to denote this vector space here by U for short. Okay, there exists this convex polytope and a real analytic diffeomorphism. Right, which I'll denote by phi of Tj from the Hitchin component to this convex polytope. Okay, so I should make a few comments here. So remember I mentioned that the Hitchin component was of dimension n square minus 1 times 2g minus 2. Right, so since this is a diffeomorphism, this convex polytope inside of U is necessarily of codimension k times n minus 1. Okay, so in other words, this guy is cut out by k times n minus 1 linear equations and a bunch of linear inequalities, right? That's what it means to be a convex polytope. Okay, so again, this is not just an existence theorem, right? Everything is explicit. What Bunohan-Duggar did is they found explicitly this number of functions on the Hitchin component, okay, given T and J. And so you get a map from the Hitchin component to this vector space U, and they characterize the image of this map. Okay, they show that it's injective, and they characterize the image. So they specified the linear equations and inequalities that cut out this convex polytope for you. Okay, so again, everything is explicit. Okay, and then what we did was we modified their parametrization phi tj, okay, to get another real analytic parametrization. So another real analytic diffeomorphism, which I'll denote by omega tj, from the Hitchin component to the same convex polytope. Okay, so I'm giving you another parametrization of the Hitchin component by this same convex polytope, but the parametrizing map is different. Okay, and the reason I want to do this is so that the following theorem is true. Okay, so I'm going to let Wt inside of U, right, be the n squared minus 1 times 2g minus 2 dimensional subspace containing the convex polytope Pt. Okay, so I said that the convex polytope was cut out by k times n minus 1 linear equations and a bunch of linear inequalities. Okay, I forget about the linear inequalities. This k times n minus 1 linear equations cut out a vector subspace of U, and the vector subspace is Wt. Okay, so this is the smallest subspace of U that contains the convex polytope. Okay, then theorem says that the map from this vector space, Wt, to the set of Tj parallel flows. Okay, so what is a Tj parallel flow? It's an integral flow of a Tj parallel vector field. Okay, so now I'm gonna define what this map is for you. Okay, so I take any vector in Wt. I need to assign to this vector a flow on the Hitchin component. Well, what do I need to do to define a flow? I need to say if I pick any point in the Hitchin component, and you give me a time parameter t, right? I need to give you a new point in the Hitchin component. That's what a flow is. Okay, and the new point is obtained in the following way. First, I apply this parametrization map omega tj to my representation. Okay, so this is now something that lives in the convex polytope. Okay, and then I add t times mu to it. Okay, so for sufficiently small t, right, this guy still lives inside of the convex polytope, right? That's what, that kind of follows from the definition of Wt. Since this guy is still in the convex polytope, you can apply the inverse map to get another point Hitchin component again. Okay, so this is my flow. And the claim here is that this map is a linear bijection. Okay, so there's a natural linear structure on this space of Tj parallel flows. Okay, because if you take any two Tj parallel vector fields and you add them together, you get another Tj parallel vector field. If you take a Tj parallel vector field and you scale it, you get another one. Okay, this just comes from properties of parallel vector fields with respect to some flat connection. Okay. So the claim here is that whenever you give me a vector mu in Wt, and I define a flow this way, this guy is a Tj parallel flow. Okay, it's an integral flow of one of these Tj parallel vector fields. Furthermore, every Tj parallel flow arises this way. Okay? So if you combine Theorem 1 and Theorem 2 together, right, you can say quite a bit about the symplectic structure on the Hitchin component. Okay, so the first thing you can say is that every TJ parallel flow is Hamiltonian. Okay, so theorem 1 tells you that every TJ parallel flow is symplectic, right? Because as you flow, you preserve the symplectic structure. But then once you combine that with theorem 2, right, basically you need to know that any two TJ parallel vector fields commute. Then you can use that to construct Hamiltonian functions for these flows. Okay, so you can, so that's the first corollary. And then using the first corollary, now you can make the following statement. Okay, for any Hence decomposition, P of S, okay, we can construct a global Darboux coordinate system. For the Hitchin component equipped with the Goldman symplectic form. Okay, and this is extremely explicit as the Fenton-Newton coordinates on Teichmüller space. Okay, right, and furthermore, when you do our construction, in the case when V equals to R2, yes. Yeah, so yeah, when you take a density composition, I make some choice, okay, and the choice is basically, I don't know, the obvious choice of gluing two ideal triangles to get a three-hole sphere, okay. Yeah, and then you need to okay, so here I'm lying a little bit. You need to make some choice of how to normalize the. I mean, even in Wolpert's theorem, when you choose a Pence decomposition, you get Fenton-Newton coordinates. You need to make some choice of normalization of how to glue your pairs of Pence together. Okay, so you need to make that same choice here, and that's basically the role of the bridge system. Okay. Yeah, and when V equals to R2, this recovers the Fenton-Newton coordinates. Okay, so this gives a complete generalization of Wolpert's theorem to the setting of Hitchin components. And also, I should point out that unlike the first statement, the second statement is not just a trivial consequence of Theorem 1 and Theorem 2. From Theorem 1 and Theorem 2, you need to still make some computations in order to get this statement. Okay. However, the computations are simple enough that you can do by hand. Okay? You don't need to rely on a computer to do this. Okay. Right, so these are, okay, this is the result that we proved. Okay, so I guess in the remainder of my time, I would like to say a few words about the proof of both Theorem 1 and Theorem 2. Okay, and the main thing I would like to describe is what are these TJ parallel flows? Okay, these are kind of the central, this is part 4. These are the central objects that we study, really. Okay, and in fact, you can interpret Theorem 1 and Theorem 2, yes, they're both on the board, okay, as a description of these TJ parallel flows. Okay, Theorem 1 describes them in terms of the symplectic structure on the Hitchin component, and Theorem 2 describes them in terms of a real analytic parametrization. Okay, but I did not tell you what C of TJ is, and I did not tell you what omega of TJ is, right? So I have not actually told you what these flows look like, okay? And now I hope to give a geometric description of what these flows look like. So in order to tell you how to define these flows, I need to rely on this theorem that is obtained by combining the work of François Labourie and Olivier Guichard. Okay, and what they say is the following. The PSLV Hitchin component is canonically in bijection with the set of Frenet curves from the boundary of gamma to the space of complete flex in V that are rho equivariant with respect to some representation rho from gamma to PSLV. Okay, and I'm going to consider these curves up to PGLV. Okay, and this set naturally sits inside of the space of Frenet curves from the circle to the space of complete flags. Okay, again, consider up to projective transformations. Okay, so there's a lot going on here. I'm going to try to explain everything piece by piece. Okay, so first, what is a flag, right? A flag, let me try to write it somewhere here. Where's that? A complete flag is a nested sequence of subspaces in V, one of each dimension. Okay. So when I have a complete flag F, right, is the data is a bunch of vector spaces inside of one another, right? Okay, so that the dimension of Fi equals to I. Okay, so I will use this notation whenever you give me a flag F, okay, the ith dimensional subspace of V determined by this flag is going to be denoted by F to the I, okay? So the set of all these things, right, is what F of V is, okay, and this is a real analytic manifold, naturally, okay? So here I'm considering maps from the circle into the space of flags that are Frenet. Okay, so what does this word mean? Well, I'm not going to explain to you precisely what it means, right? But you can think of this as saying that these curves have a very strong transversality and continuity properties. Okay, as far as this talk is concerned, this is enough. This is all you need to know. Okay, so I've explained what's going on here. Now, what about here? So gamma here was the fundamental group of my surface S. Okay, and as Kasra told us yesterday, this is a Gromov hyperbolic group. So you can take its Gromov boundary, right? That's what partial gamma is. Okay, and this is also known to be topologically a circle. In fact, Kasra essentially gave us the proof yesterday. Okay, and so it makes sense to require a map from this topological circle into the space of flags to be Frenet. Okay? Now, the advantage of using partial of gamma here in place of S1 is that now I have a natural gamma action on its boundary. Okay, so now it makes sense to require this map to be equivalent in respect to this representation, right? Because you have a PSLV action on the space of flags by projective transformations. Okay? So this guy sits inside of this space, right? Because all I'm doing is imposing this additional row equivalence property. Okay, and I'm going to call this the Hit VS locus in the space of Frenet curves. Okay. Let's see, anything else I need to say? Okay, so another piece of notation. I'm always going to denote the set of Frenet curves from the circle to the space of flags by FR of V. Okay, so this side is FRV, consider up to projective transformations. Okay, so what this theorem is saying is that instead of thinking of the Hitchin component as a space of representations, right, I can think of it as a space of maps of curves from the boundary of gamma into the space of flags that are continuous, and very transverse, and are also equivalent with respect to some representation. Okay, so maybe this statement might look very, very strange to you, okay, but let me say what it is saying in the case in Teichmüller space when V equals to R2. Okay, so when V equals to R2, this is simply saying that the Teichmüller space is canonically in bijection with the set of continuous injective maps. C from the boundary of gamma into RP1, right, which is the space of flags when V is R2. Okay, that is row equivalent with respect to some representation. Right, I'm going to consider this up to PGL2R, up to projective transformations. Okay, and this really is the boundary map of the, whenever you take a representation Teichmüller space, this is the holonomial of a hyperbolization, and this is the boundary map of the hyperbolization. Okay, the fact that when you have a representation that preserves a continuous injective map, right, is enough to ensure that this representation is discrete. Okay, so you should think of this statement as the higher rank souped up version of this well-known statement here, okay? Okay, so with that theorem, right, the strategy to produce flows on the Hitchin component is first to produce flows on the space of Fourier curves, and then use that to produce flows that preserve the Hit VS locus in the space of Fourier curves. Okay, so that's what we're going to do now. Any questions so far? Okay, to produce flows on the space of Fourier curves, right, and first need to explain to you some very special projective transformations. Okay, so I'm going to let F, G, H be a triple of complete flex, okay, such that the I-dimensional piece of F plus the J-dimensional piece of G plus the K-dimensional piece of H is V. Okay, for any triple ijk of integers from 0 to n minus 1 that sum to n, right, which is a dimension of V. Okay, so I'm picking a triple of flex that are as transverse as possible. Okay, that's what this is saying. Then now for any time parameter t, okay, I'm going to specify a projective transformation for you, okay, which is denoted by B, ijk, FGH, T. Okay, so to give you a projective transformation, what do I need to do? I need to give you a linear map from V to V that has non-zero determinant. And then you take its projective class, that gives you a projective transformation. Okay, so I need to tell you what this linear map is. Okay, so this linear map B of ijk, FGH, T. When I restrict it to the ith dimensional piece of F, this is just the identity. Okay, I take this linear map and I restrict it to the j dimensional piece of G. This is e to the t over 3 times the identity on Gj. And if I restrict it to the k dimensional piece of H, right, this is e to the minus t over 3 times the identity on Hk. Okay, so another way to say this is that this is the linear map from V to V, whose eigenspaces are Fi, Gj, and Hk, corresponding to eigenvalues 1, e to t over 3, and e to the minus t over 3. Okay, nothing very complicated going on here. This is clearly an invertible linear map, so you can take its projective class, and that gives you a projective transformation. Okay, so for the rest of the talk, I'm going to be lazy, and I'm going to drop the square brackets. Okay, so I'm just going to use the linear map to represent its projective transformation. But when I write that, I always mean the projective transformation. Okay? Okay, so another piece of notation. So when k equals to 0, so let me just write it here. Okay, if k equals to 0, right, then I'm just going to denote b of I n minus I 0 of f g h t by b of I n minus I f g t. Okay, so if there's no h dependence, I'm just going to drop h from the notation. All right, so with these projective transformations, we can now define the flows. Okay, the first family of flows are flows associated to triples of points on the circle. Okay, so you take any triple of points x, y, z in the circle. Okay, such that x is less than y, less than z, less than x. Okay, so what do I mean by this? So my circle comes equipped with a natural clockwise orientation. Okay, and all I mean is that the triple of points that I pick, right, lies in the circle in this clockwise orientation. Okay, so for any triple like that, and for any time parameter t, I'm defining a flow, right? So I need this time parameter. And for any triple of integers, positive, okay, that sum to n. Okay, I can define a flow which I'm going to denote by epsilon of ijk, xyz, t. okay, from the space of Frenet curves to itself. Okay, by the following. So I look at epsilon ijk fght and I'm going to feed this guy a Frenet curve. Okay, since this is the space of Frenet curves, this new object here is another Frenet curve. Okay, I'm going to tell you what this new Frenet curve is by telling you where it sends every point on the circle. Okay, so if I evaluate this Frenet curve at some point W on the circle, okay, then this is going to be equal to B of ijk cx cy cz t times C of W if W lies in the interval from Y to Z. Okay? Okay, so what the hell is going on here, right? So first, what is this interval YZ? Okay, that is the set of points on the circle from Y to Z in the cyclic orientation that I've chosen. Okay? So what I'm saying is you take any point in this interval, what is the flag that this new Frenet curve sends it to? Well, first I send it into the space of flags using my original Frenet curve, and then I hit it by this projective transformation. Now, the Frenet property of C is what is ensuring that Cx, Cy, and Cz are transverse enough so that these projective transformations are well defined. Okay? So you have this. So I've told you where to send all the points here. Okay, now what about the points from Z to X? Well, you do a similar thing. Okay, first you send the point into the space of flags using your original Frenet curve C. And then now you hit it by this other projective transformation, right, which is B of jki cy cz cx of t. Okay, so what I've done is I've cyclically permuted the superscripts and the subscripts. Okay, but what is this really saying, right? These two projective transformations are going to have the same eigenspaces, but the eigenvalues have been cyclically permuted. Okay? So that's what you do for all the points here. Now for the remainder of the points, what do you do? Any guesses? Okay, it's the obvious thing, right? You do the same thing, I said you cyclically permute the superscripts and the subscripts one more time. Okay, I'm not going to write that down, okay? So this is what the new Frenet curve is, okay? And we call this flow the elementary eruption flow. Okay, for reasons that well, if you're interested, I can explain later, but it's going to be too much to try to explain that now. Okay, so these are called the elementary eruption flows. Okay, so these are the first family of flows that I defined on the space of Frenet curves. Now there's another second family of flows that's a little bit simpler, but it's very similar in nature to this, okay, which are associated to pairs of points in the circle instead of triples of points. Okay, I'm going to do that quickly. So you take any xy in the circle, such that x is not equal to y. You take any time parameter t, okay, and you take any integer I from 1 to n minus 1. Okay, then you can define this flow, which I denote by C of I n minus I, xy, t, from the space of Frenet curves to itself again. Okay, by the following formula. Okay, C of I n minus I, xy, t, when I evaluate a Frenet curve to this flow, this gives me a new Frenet curve that sends the point W in the circle to B of I n minus I, Cx, Cy, t over 2 times C of W. Okay, if W lies in the interval xy, okay, and it sends this to B of n minus I, Cy, Cx of t over 2 times C of W if W lies in the interval Yx. Okay, so what I'm doing here is the same as before, right? This is my circle with my clockwise orientation. and I have 2 points, x and y. Okay, so I'm going to map, so whenever I start with a Fermat curve, right, and I apply the flow to it, what is the new Fermat curve? Well, I send this circle into the space of flex using my original Fermat curve. And then for the points on the right, I'm going to hit it by a projective transformation, which is this guy. And the points on the left, I'm going to hit it by another projective transformation, which if you check the definition is just the inverse of this guy. Okay, so in the case when V is RP1, right, what am I doing? Right, I'm mapping the boundary of my group into RP1. I choose 2 points. I'm hitting the left side by a projective transformation that fixes those 2 points, and the right side by its inverse. Okay, so this is doing a shear of hyperbolic space, right, when I view RP1 as the boundary of H2. Okay, so we call this the elementary shearing flows. Okay, so informally, you should think of these flows as telling you how to move in the space of Fermat curves. That's kind of that. This should be like analogs of shearing in Teichmüller on hyperbolic surfaces, and this is basically telling you how to change what an ideal triangle looks like. So on in hyperbolic space, right, any ideal triangle is the same with anything else, right, using a projective transformation. So these kind of objects do not exist. But in the higher rank setting, you must add these things in. Okay? All right, so these are my flows. And then there's a little proposition you need to check here. Sorry? Exactly. That's the point. Okay, you're skipping ahead. But I'll get to that soon. Okay. Okay, so first proposition to check, right, is that first, okay, you need to show that these are well defined. Okay, meaning that this definition I give you actually defines a Fermat curve. So right now it doesn't even look continuous. Okay, but it turns out that it is, and in fact it's Fermat. Okay, so that's something you need to check. And the second thing you need to check is that they descend to flows on the space of Fermat curves consider up to projective transformations. Okay, so what you need to check here is that the flows commute with the action of PGLV on the space of Fermat curves. Okay, then once I have flows here, I want to get flows that preserve the hit VS locus, right? So you want to, step 2, use these to get flows on the Hitchin component. Okay, and as Mahan pointed out, the problem here is if I try to just apply one of these elementary flows, right, you're going to break any kind of row equivalence you had, right? Even if you started off with a curve that has some row equivalence. Okay, so that's the problem. So the elementary flows do not preserve row equivalence. Okay, so the solution to this is where the ideal triangulation comes in. So the idea is to apply, so perform the elementary eruption and shearing flows using the ideal triangles and edges of the ideal triangulation T. Okay? So what do I mean by this? So here's a picture of the universal cover of my hyperbolic surface again. Okay, and on this guy, I had my ideal triangulation, right? It's really bad. Okay, so you have your ideal triangulation that looks something like this. something like this. Now you pick any ideal triangle you want. So you take this guy, for example. Okay, and this guy specifies 3 points in the boundary of gamma for you, and you can use these 3 points to perform your elementary eruption flow. Okay, but this does not preserve row equivariance. So what you do, you look at the gamma orbit of this triangle. Okay, so this guy here, say you maybe something like this. Okay, and then for each of these ideal triangles, you perform the same elementary eruption flow. Okay, on the entire gamma orbit. Similarly, if you have an edge of the ideal triangulation, that gives you 2 points on the boundary of gamma, and you can perform an elementary shearing flow. Okay, but that doesn't preserve equivariance again, so you need to do the same flow on the entire gamma orbit of that edge. However, this naive idea introduces a new problem, a whole can of worms. Right? Because what do I really mean when I say you perform these elementary shearing flows on the entire gamma orbit? Right? What I'm doing is I'm composing infinitely many of these guys together, right? One for each ideal triangle. And generically, this does not converge. Okay? So the magic that somehow makes everything work, right, is you can use the choice of a bridge system to make sense of this. Okay, so use J to make sense of this. Okay, I mean, the basic, I mean, this is really one of the most technical parts of the paper, so I'm not going to be able to explain it in any reasonable way in this talk. But you should think of this as saying, I mean, when you try to do this process, right, the closed edges are where things are locally infinite. Okay, so that's where all the mass happens. And so this bridge system helps you make some choices on what to do when you get close to the closed edge. That's the basic idea. Okay, and so using this procedure, right, then the set of convergent flows that you can construct this way are the TJ parallel flows. Okay, so these are the TJ, you get the TJ parallel flows. Okay, so yes. No, on all edges, Right, you must allow, yeah, you can do it on any edge. So that, yes. Yes, so that is related to theorem 2, right? Which again, you're jumping ahead, right? Okay, but okay, maybe before I go there, let me just say this. I still have not told you what the TJ parallel flows look like, right? But at least I hope to convince you that, you know, if you pick a particular ideal triangle of your surface and you look at what happens to it under the TJ parallel flow, you know what it looks like. It's some combination of applying the elementary eruption flows to this triangle. Okay, and if you take an edge, right, when you apply a TJ parallel flow to it, it looks like you're performing some combination of these elementary shearing flows along your edge. Okay, but there's a global picture that you need to deal with when you want to try to prove the convergence, okay, of everything. Anyway, yeah, so once you have this, then you need to relate this, right, to the parametrization. So that's step 3. Okay, and this step, I cannot explain it to you again, right, because I did not tell you what the parameters of the Bunohan-Duggar parameterization are of these guys. Okay, but I mean, to kind of make this, maybe make it a little bit more believable how you can do this, the way that Bunohan-Duggar constructed their parameterization is also using the Labourie-Guichard theorem. Okay, and since I have an explicit description of the flows in terms of the limit maps, the Frenet curves, maybe it's not so unbelievable that this description of the flows tells me how I should reparameterize the Bunohan-Duggar parameterization to get this parameterization where theorem 2 holds. Okay? Let me just leave it at that. Okay, and once you do this, you get theorem 2. Okay, so I went a little slower than I thought I would. Okay, so I have, this is this plus 5, right? Okay. Okay, so maybe the last 10 minutes, I will say a little bit about how to prove theorem 1. How do you relate these TJ parallel flows to the symplectic structure on the Hitchin component? Okay, so to prove theorem 1, okay, the crux is the following. Okay, you need to show that for any Tj parallel vector fields, x1 and x2, okay, the symplectic pairing between x1 and x2, right? So I'm pairing two vector fields. This gives me a function on the Hitchin component. You need to show that this is the constant function. Okay, once you do this, then it's not so hard for you to construct the symplectic trivialization C of Tj. Okay, there's some work to do, but it's not so bad. Okay, once you know that they all symplectically pair to constants. Okay, so I need to figure out a scheme to explicitly compute what the symplectic pairing is. Okay, if you give me two vectors at a point in the Hitchin component, how do I symplectically pair them? Okay, so to do that, you need to give me I need to give a description of the first cohomology of a surface with coefficients in this twisted bundle in a way that makes it easy for me to compute things. Okay, so you need to describe, let's just say, the tangent space at a point of the Hitchin component. Okay, and maybe in the remainder of my time, all I can really do is give you this description. And I will leave, I'll just say that once you have the description, you can compute the symplectic form. Okay, now to give this description, right, we introduce another topological object on the surface, right, which is what we call a barrier system. Okay, so I'm going to let B be a barrier system. On S associated to the ideal triangulation T. Okay, what is this object? So just like the ideal triangulation and the bridge system, right? This is a purely topological object. Okay, but if you choose a hyperbolic metric on a surface, then it becomes realized as a geometric object on your surface again. Okay, so here is the universal cover of my surface. And I had my ideal triangulation. Right? So you have something that looks like this. Okay, so you might have some closed edges around as well. And then you have these isolated edges accumulating onto it. Okay, something like this. Now, the first thing you need to do is you need to choose an orientation on every edge of your ideal triangulation in a gamma invariant way. Okay, but you make any such choice. So let's say you have something that looks like this. Okay, something that looks like this. Okay, you make such a choice. Then, I need my other color. For each of these hyperbolic triangles, you take its barycenter. Okay, and then from the barycenter, you fire off geodesic rays to the vertices. Okay, and you orient this geodesic rays outwards. Okay, like this. Okay, so this is what I call a barrier system. Right? It's a collection of oriented geodesics and oriented geodesic rays constructed from your ideal triangulation this way. Okay, so with this topological choice, I would like to describe a co-cycle representative for every cohomology class in H1 of S with coefficients in this twisted bundle. Okay, so I'm going to take a path rho t in the Hitchin component that's smooth. Okay, and then this gives me a path of Frenet curves, Ct in the space of Fourier curves, consider up to projective transformations. Right? This was again the Labourie-Guichard theorem. Okay, so what do I want? I want a co-cycle representative of the derivative at t equals to 0 of this path rho t, right, which I'm thinking of as a tangent vector at rho naught, right, which is the same thing as the first cohomology of your surface with coefficients in SLV twisted by add of rho naught. Okay. So how do I produce, what do I need to do to get a co-cycle representative? I need to give you a way to assign every one simplex in the universal cover a Lie algebra element in a way that is equivalent with respect to add of rho naught and also satisfy the co-cycle condition. Okay, so let's say I pick this one cycle. This guy. Okay, what is the Lie algebra element I assign to this? Well, you can see, right, you look at the backward endpoint, it lies in this fragment of the ideal triangle. Okay, so this determines 3 points on the boundary, this point, and this point here. Okay, you just look at the ideal triangle that it lies in. Okay, and then these of the 3 points, these two are special because they are vertices of this fragment as well. Okay, so you have something like this. And then you look at the forward endpoint, you do the same thing. Ooh, okay, they don't tell me how much time I have left now. Okay, something like this. Okay, I'm just going to denote this by x, y, z, and then this is x prime, y prime, z prime. Okay, then now, okay, so I'm going to be across the room. So, but you should look at that picture still. I'm not going to go beyond this board, right? So we're almost done. Okay, then for any t, okay, you choose a representative CT in this projective class of Fourier curves, okay, such that CT of 1 of x equals to C0, 1 of x. So remember, CT of x is a flag. I'm taking the one-dimensional piece of the flag. They're requiring this to be same. And then CT of y equals to C0 of y, and CT of z equals to C0 of z. Okay? Every projective class of Fourier curves has a unique representative like this. Okay, this is just a property of the action of PGLV on the space of flags. Okay, given any two flags in a point that are sufficiently transverse, and any other two flags in the point that are sufficiently transverse, there's a unique projective transformation that takes that to this. Okay, so you can find something like this. Okay, then I'm going to let GT be the projective transformation, okay, so that GT times C naught 1 of x prime equals to CT 1 of x prime. Okay, GT times C naught of y prime equals to CT of y prime, and GT times C naught of z prime equals to CT of z prime. Okay, by the same principle, there's a unique projective transformation so that this is true. Now, when t equals to 0, this is the identity projective transformation. Okay, so what is the Lie algebra element I assign to that guy? Right, you take the derivative at t equals to 0 of this group element GT, and this is an element in the Lie algebra. Okay, so this is the Lie algebra element you assign to that one simplex. Okay, you do this, and then there's some other stuff you need to do, but basically with this, you can explicitly compute what the Goldman symplectic pairing is. Okay, so I should stop here. Thank you very much. Yes. Was it Labourie? I don't know if it's Labourie who did this. He described that in terms of geodesic currents.
Yeah.
Yeah. So, but Bunohan and Dreyer also have a description of the tangent of the tangent space to the Hitchin component by using real valued cocycles, not Lie algebra valued cocycles.
Yeah, so that was my point. I mean, so as cross ratios, yes, I think.
Yeah, cross ratios. That's Labourie then. Yeah.
Yeah. So is there a relationship? I think that's.
Yes. So if you look at the parametrization omega tj, that I did not tell you what it is, right? The functions you use to define the parametrization involve the cross ratio. So it's secretly embedded in there somewhere. Okay.
So can you say a little bit about what the additional computation is that's needed for the global Darboux coordinates?
Okay, so maybe I can explain to you privately later because this is a little bit technical and yeah.